stand out here and not at the mic? Can you hear me in the back? Okay, because I can't be corralled, I'm sorry. Anyway, thanks, Gard. I'm surprised you remembered that. I'd forgotten about that, but now it brings back some memories.
You wanted to forget about it.
I wanted to forget about it, exactly. I really appreciate the invitation and the chance to reconnect to the non-Mon community and to the KR community. Yesterday certainly brought back a lot of memories. Vladimir's talk and Lior's talk especially. Okay. Do I need to hold the mic? Can everybody hear me?
The recording is
you're
recording as well.
Oh, the recording with this though,
Yeah, okay.
not with this. Okay. So, it reminded me of my first non-Mon reasoning workshop in 1990 at the Stanford retreat. There was a history of doing these things out in the middle of the woods. Ray Ryder and I arrived very late that night, and it's a small facility, so everybody had to have roommates. So I walked into my room, and who was there sitting up in bed reading a book? John McCarthy. Right? So that was my introduction to John McCarthy, a little bit intimidating for a green graduate student. Anyway, and it also made me think a little bit about the last time I was at the KR conference, and I had to do a lot of thinking, and I couldn't exactly remember, so I had to look it up. And it was in 1994, 18 years ago, sadly. Time really flies. I gave a talk at that workshop on a paper called Toward a Logic for Qualitative Decision Theory. That was a bit of a foreshadowing. I kind of dropped a lot of the qualitative, not completely, and jumped into the decision theory and did a lot of work, as Gerd has mentioned, in, say, Markov decision processes, probabilistic inference, reinforcement learning. I'm very interested in game theory, mechanism design, and economic models. And from, say, mechanism design and economic models, I started to work in social choice over the last couple of years. And it's kind of brought me full circle, because you'll see that a lot of the models that we use are much more qualitative, in particular the models of preferences. So it's something that I think hopefully will resonate here. And there's a lot of opportunity for bringing KR to the party when we talk about solving these types of problems. Okay. So what I want to talk about today, as I mentioned, is social choice. I'm going to feel very schizophrenic here. This is some work that I've been doing. Most of this work I'll describe is joint work with my PhD student, Tyler Liu. It's an area we're very excited about. There are two things that we're trying to accomplish. First, think of social choice and argue that social choice in the more traditional vein is actually provide very strong foundations for all sorts of group decision making and group recommendation problems. And second, what we want to do is make the techniques and the models of social choice much more practically applicable. Okay? So I hope this will become clear as we move along. All right, so let me start simply by saying what I mean by social choice. I'm sure many of you are familiar with it, but for those of you who are not, in a nutshell, it's simply the study of collective decision making. Basically, think of a group of people or a population. We've got a collection of options, and we've got to choose one. For example, we've got members of a town here maybe deciding on a new recreational facility or public project. The problem is that each of them has their own individual preferences, their personal preferences over these options, and somehow we've got to aggregate these preferences to come up with a good consensus choice, something that maximizes some notion of social welfare or group satisfaction, okay? Obviously, this is a problem that's been around as long as humans have actually cooperated. It's been studied formally somewhat formally for millennia, and certainly mathematically for a number of centuries, as Jerome mentioned in his tutorial. By and large, the methods of social choice and the motivation have largely focused on high-stakes problems in electoral domains, public policy, financial and economic policy, things of that nature. But increasingly, what we're finding is that social choice is becoming important in much lower stakes than what I would call higher frequency domains. For example, you could just have a group of people deciding on a restaurant to go. Social choice is actually an appropriate model for this. Things could be more complicated. I think somebody asked this, I don't know if it was this conference or at AMIS. I think everybody here has probably used the doodle poll, okay? Right? And now we're talking about potentially more complicated combinatorial objects over which people have to express their preferences and come to an agreement. Okay? Why should we be interested in computer science in social choice? I won't go through all the details. I'll focus on our motivations. The problems in social choice, whether we're talking about winner determination, manipulation, control, various types of things, present a lot of interesting computational questions of computational complexity, approximation, communication complexity, things of that nature. It's been used widely in the multi-agent systems community. But the thing that really got us excited about social choice is the fact that now there's just tons and tons of preference data available at the drop of a hat. Whether we're talking about clickstream data from web search results, the explicit ratings data that one gets from recommender systems, we have the ability to do preference aggregation on a large scale with very, very low friction. Okay. Another thing that makes, I should say, this is something that has really brought the machine learning community to the party. There's a huge community in doing preference learning and rank learning, although they don't quite take the foundations of social choice seriously enough. Another aspect that should be of interest to KR people and certainly to optimization people is the combinatorial nature of the alternatives, whether we're configuring products, schedules, large complicated artifacts that are best viewed in terms of their multi-attribute components. Okay? So, what is our agenda? As we move to these lower stakes domains or these more complex domains, we're really placing new demands on the techniques of social choice. Okay? We need new models, and hopefully I'll make this will become clear as we move along. New models and new decision criteria to account for these new applications of social choice techniques. We're not electing members to a legislature anymore. So the focus today is just going to be on how do we minimize the amount of information that's needed to come to a good consensus choice, whatever we mean by good consensus choice. Okay? So I'm going to talk about, I was going to do 4. I'm going to lay off the learning a little bit. I'm going to talk maybe about 3 things and then a few minor extensions. I want to leave a little time at the end. So the first thing I'm going to talk about is how would you make decisions in a robust way when all you have is partial information about the preferences of the voters or the individuals in your population. Okay? Second, I'm going to talk about how you would actually go about eliciting this information from the members of your population. Third, I'll talk about how you might exploit probabilistic information or distributional information about the preferences to further accelerate the elicitation process and improve the decision-making process. Fourth, I will say maybe take 1 minute to talk about learning these probabilistic models. There's a real question of where these distributions might come from. Turns out that with a lot of this data, it's very easy to learn these distributions. And finally, I'll talk very briefly about some challenges as we move to, say, combinatorial option spaces or alternative spaces. And something that's caught my interest very recently, the idea of voting and preference aggregation in the context of social networks. All right? And feel free to interrupt and ask questions as we go along. Okay. Let me skip this. All right, I'm going to do in 3 slides what it took Jerome about 3.5 hours to do on Sunday. So I might skip a few of the details, though. Here's the brief primer on social choice. The basic idea is we have a set of alternatives. Right here are our little recreational facilities, finite set, A1 through AM. We've got some voters, or I'll call them voters, just think of them as users of some type, that have preferences over these alternatives. These preferences are represented by what I'll call a vote. It's simply a ranking or a linear ordering, a complete linear ordering, or a permutation of the alternatives. Right? So this dog lover here, she prefers to have a park rather than a tennis court, which is better than a swimming pool. Okay? I'll use the term a vote profile to talk about the collection of votes, one of these rankings for each one of my users or my voters. And our goal is simply to find an alternative that maximizes some notion of consensus or group satisfaction, however you'd like to define it. Okay? Sometimes people consider the idea of producing consensus rankings. How should this group or society rank all of the alternatives? It's an important problem, but I'm just going to focus on the winner determination problem. Okay, selecting a single winner. Okay. So we've got this idea of a voting rule. Simply takes one of these vote profiles, a collection of all of these rankings, and selects a winner. Picks an alternative from that set. Okay, that's all the voting rule is. Okay, and you're all familiar with many different voting rules. The most obvious one is plurality, where you simply count the number of times an alternative occurs in the first position in a ranking. And the winner is the one that has the maximum number of votes. The nice thing about that is people don't have to provide full rankings. They just have to say, what is my preferred alternative? That's the only thing that matters. There are other rules. You're probably familiar with the board account. The basic idea is Every time if we've got 3 alternatives, every time something is ranked in position 1 by a voter, it gets 2 points. In position 2, it gets 1 point. In position 3, it gets 0 points. We add up the scores, and we choose the winner that has the maximal score. It's often used in, say, sporting contexts and so on. We don't have to have this 2, 1, 0. Any non-increasing scoring vector for assigning weights to positions will do. Okay, so we call these things scoring rules. Okay, plurality, veto, approval of various types. They're all just special cases of these types of scoring rules. Okay. You can imagine saying, well, I don't want to maximize something. I want to be Rawlsian and make the least well-off person in my society as happy as possible. You might call that egalitarian. And again, the idea is you score a candidate by looking at the worst position they are in somebody's ranking, and then you choose the candidate that has the highest such score. Okay? So you make the least well-off person happy as possible. Okay? And of course, we could go on. That's why we had a half-day tutorial on social choice. There are many, many voting rules, many, many issues that one can define. Okay? I won't go through them all, but the one thing I want to emphasize, and this is something that Laurent Gia mentioned in his talk yesterday, one of the first talks on Monday morning. Most voting rules can be defined in terms of a natural scoring function. The basic idea is we take this vote profile, the preferences of all of our users, we take an alternative, and this scoring function says how good is this alternative for our population, given that these are their preferences, and then we choose the alternative that maximizes it. All of these rules that I mentioned here, the ones before, and many others are defined using this notion of this idea of the scoring function. Right? So think of it as a measure of societal satisfaction or utility or social welfare. Okay? Okay, so now what do we want to do with all this? That's a primer on social choice. You might ask yourself, why don't you see these complex voting schemes where people submit full rankings over alternatives? Why aren't they used more often in practice? Occasionally, some people use voting rules like STV, single transferable vote, and so on. And you might ask yourself, why does Doodle only use approval voting, right? The real issue in our mind, it's going to be especially important as you move to lower stakes domains where people don't want to put a whole lot of thought or effort into ranking alternatives, is simply the cognitive complexity and the communication costs of ranking precisely a whole bunch of alternatives, okay? Increasingly, when people are using these methods for judgment aggregation and human computation and crowdsourcing and things like this, there are actual monetary costs to getting people to ranking alternatives. Okay. Suppose instead we could elicit just partial information about people's preferences, but the right partial information and just enough partial information to make a good decision. Suppose that in these low-stakes domains, we don't even care about finding the winner. We just want to find somebody that's good enough, so we don't spend a lot of time thinking about our very precise trade-offs. That might make the techniques of social choice much more applicable in practice. Whether you want to choose presidents this way, I don't know, but it might be a good way to choose restaurants and schedules and things of that nature. Okay? So, high level, everything that I'm going to talk about today can be viewed with this lens. We're going to think about voting protocols with approximation. Basic idea is we're going to take some of the voters, we're going to ask them a few queries, we're going to see, do we have enough information to determine a decent winner? Okay, something that's good enough. If not, we'll pick a few more voters, ask them a few more queries, and keep going until we're satisfied with the result, where satisfaction is something that you get to choose. Well, you get to choose your degree of approximation. Okay? Now, theoretically, we know this won't save us very much. There are communication complexity results on various types of voting rules. For instance, Borda, which I'm going to use a lot today, that basically say you cannot, in the worst case, determine the winner of a Borda election without everybody revealing basically everything about their full preference relation, their full ranking. Okay, but we're not concerned about worst case communication complexity results. We want to know, can we actually get some savings in practice when we want to use these things in the real world? Okay. Any questions so far? Hope the picture's relatively clear. Okay. Just one little bit of notation. I'm going to talk about partial votes to be any collection of pairwise comparisons that are consistent. So it's basically any partial order over the alternatives. This voter, for instance, has told us he likes A better than B, E better than D, and told us nothing else. Okay, so it's just a partial order. okay? These collections of pairwise comparisons will be able to represent just about anything that you might naturally ask a voter to reveal, okay? Click. Block here, okay. Partial vote profile is simply a collection of these partial votes, one for every voter. And we'll talk about this idea of a completion. It's just any way of extending a partial vote into a complete order. Okay? It's any linear ordering, total ordering that consistently extends a partial vote. Okay? All right. So, first question we're going to ask, so before we get into elicitation, is suppose I had a partial vote profile, this set of pairwise comparisons from all of my voters, not a complete ranking, and I had to determine a winner. Suppose this is all the information I had from a data source. Okay? We're going to propose a particular means of selecting winners. This is something that doesn't get enough attention in social choice. How do you make decisions when you've got incomplete information? I'll show you an illustration of this, but we're going to use a notion known as minimax regret. I'll define it formally, but the intuitions will become clear on the next slide. We're going to define, suppose now I give you a complete vote profile, no uncertainty, no incompleteness. So this is V. And suppose I were to choose an alternative A. Okay, I'm going to say that the regret or the loss associated with choosing alternative A is just how bad it is relative to the true winner. Okay, what is the difference between its score and the score of the true winner, the thing that maximizes my scoring function? Okay. Of course, we don't actually know the vote profile. All we've got is partial information in the form of a partial profile P. So ignore the top line, the PMR line. I'm going to say that the maximum regret of my alternative is simply the worst case loss under all possible realizations, all possible completions of the vote profile. So if I pick an alternative A, an adversary is going to come along and complete everybody's preferences in such a way that I regret my choice as much as possible. It's going to be as far from optimal as an adversary could make it. And in the presence of such an adversary, what I want to do is choose the alternative that has minimum max regret. Okay? So hopefully that's very clear. It may not be. I know a bunch of you were out late last night. So let me just illustrate it with a simple little example. Suppose we've got these partial vote profiles. The dog owner is ranked nothing. The tennis owner likes the tennis court better than the pool, but it says nothing about the playground and so on. Okay? If we were to choose, I forget what it is. The tennis court. If we propose the tennis court as the winner, how bad could that be? Well, if you want to make it look as bad as possible, you would arrange the preferences in this way, and you'd end up with, if we're doing border voting, the border score of the tennis court would be 2, the border score of the park would be 4, and we would regret our choice by 2 border points. Okay, 2 points in this measure of social welfare. By contrast, if I had proposed the pool as the winner, okay, it turns out that would be even worse, okay? An adversary would come along, or this is a possible completion of the vote profile, and what that does is makes the tennis court look really good, as a border score of 6. The pool has a score of 2, and we would regret that choice, okay? The park is symmetric. So obviously, what we want to choose here to be robust against this uncertainty is the tennis court. It has the smallest maximum regret, okay? So hopefully the intuitions are clear. All right, so why do we want to use minimax regret? Well, first of all, it gives you very natural robustness criteria, and it gives you the tightest possible error bounds relative to this vote uncertainty, this preference uncertainty. If minimax regret is 0, it should be obvious. You've got the optimal answer, and you don't need any more information. And I won't say much about this, but even though I'm a Bayesian at heart, there's a lot to recommend this approach in relative to Bayesian methods. Bayesian methods are actually very difficult computationally. We have to have priors and update distributions. And usually that can't be done in closed form. Okay? So, I'm going to skip this just in the interest of time and now talk about, that all sounds good in principle. How would you go about computing the minimax optimal solution, given these partial vote profiles in say, large domains? So we've done a lot of work using minimax regret for single agent decision making and preference elicitation. I'll say a few words because I think that connects to the KR community reasonably well. But you can't formulate these problems as mixed integer programs. You just end up with way too many variables. I won't get into the details. But it turns out that you don't have to. It turns out for at least for a lot of voting rules, you can compute minimax regret very, very effectively. Okay? What we're going to do, here's the basic framework. Think about computing this quantity, I'll call it the pairwise max regret between A and W. So if I give you a partial vote profile P, and I propose an alternative A, you can ask her, and suppose I had an adversary that wanted W to win instead of A. The pairwise max regret is, given this partial profile, how much better can the adversary make W look than A? We're not allowing the adversary to pick anything. He can only try to maximize the advantage of W over A. Okay? So I'll just compute one of these tables, right? We've got M squared entries here, if I've got M candidates, and I'll choose the alternative that has minimax regret. Okay? So the question now is, how can I compute the entries of these tables? How can I compute the pairwise max regret between an alternative A and a candidate W? Okay? And it turns out that this can be done in polynomial time for a number of different voting rules. And I want to illustrate it just using the border rule, just to get the intuitions across. Okay? Skip that. All right, so here's the picture. And I don't know how to do this. I'm going to have to talk like this because I want to point at these pictures. The basic idea is to complete the partial profile, extend it into a complete profile for every one of these voters individually, okay, but without actually explicitly doing it. All right, so there are only 3 knowledge situations that we can be in. Either the voter has told us A is better than W, okay, that's the first case, W is better than A, or W and A hasn't compared them yet, okay? And then all other candidates are arranged in these little blobs, okay? Doing this, right? These little blobs. So here we've got a bunch of candidates that are better than A. Here are candidates that are worse than A but better than W, and so on. Okay, worse than A and better than W. Okay. Now the question is, in each of these cases, what would an adversary do to maximize the advantage of his candidate W over my proposed candidate A? Okay. And I'll illustrate it just with one of these cases because the intuitions are pretty clear. All right. So suppose I propose A. We've got this voter who has given me very partial information. We know that he likes W better than A, and the adversary wants to make W look as much better, give it as much advantage over A as possible. Well, what the adversary would do is take all of the candidates arranged in this set F right here, and put them somewhere between W and A. Right? Extend the advantage of W over A. Same thing with the set U. Same thing with the set E. Okay. So if we look at the contribution to pairwise max regret of this particular voter, it's simply the cardinality of these particular sets. Okay, so you don't actually have to compute the order. All right, and the same thing happens with the other cases. Right, it's basically just organizing these partial orders and counting the number of elements. Okay, so this shows us that basically we've got an NM squared algorithm for abortive, for most positional scoring rules. And so on for computing minimax regret, which makes it feasible to use in practical domains. Okay, and then you can do the same thing even if the rules aren't decomposable, even if how you complete the ordering for one voter depends on how I complete it for another voter. For certain rules, you can do this in a way to make these things polynomial time. Now, not all rules can be tackled this way in polynomial time. Some are NP hard, but a lot of common voting rules can be tackled this way. All right. Oops. Okay. So, how does this do? Well, we'll talk about it in a few minutes. Before I get there, what I want to now move into is the idea of vote elicitation. Okay. This tells us, given a partial vote profile, what decision should I actually make? Okay. Now the question is, suppose I do this computation, I get the robust winner, the minimax optimal winner, I look at its maximum regret and say, that's too high, I'm not satisfied with that possible, with an error of that degree. Okay. The only thing that I can do is elicit more information from my voters and try to reduce that regret. Okay. So the question becomes, how should we do this? All right? So a very simple heuristic strategy that seems to work quite well in practice, at least on the data sets that we've looked at, is something called the current solution strategy. It has a very natural intuition. Okay. The idea here is when I solve this minimax problem, I get a solution, let's call it A star, and I get an adversarial witness, W, the thing that the adversary holds up to say, here's how bad your candidate could be. Okay? So what we're going to do is say, well, look, if we're going to ask some voter some query, we had better do something to reduce the advantage of W, the adversary's candidate, over my candidate, or else I'm not really going to make progress in tackling the minimax regret. Okay? So how should we go about doing that? Okay. Well, we'll look at all of the voters. Okay. And we're going to find for each one of them the query that has the potential to reduce that advantage of W over A as much as possible. Okay. You can't guarantee that you can reduce it because you don't know what the answer to the query is going to be. Okay. And then we're going to choose the voter and the query that has the maximum potential. Okay. And how would you go about doing this? I'm going to illustrate the intuitions just for this one simple case, just so you get a rough idea. Okay. So let's take this case where we have a voter who's already told us they like W better than A. There are a bunch of candidates arranged in these other blobs here. Okay. And what are some reasonable queries that you might ask of this voter? Okay. What we're trying to do, remember what the adversary is going to do. He's going to take all of the candidates in these blobs and put them between W and A to maximize that gap. What we want to do is tie the adversary's hands and prevent him from doing that. Okay? So a natural query might be to say, well, take some candidate in this blob F and ask, do you like A better than F? Okay? So this is this little F here. Do you like A better than F? Okay? If he answers yes, if the voter answers yes, what happens? Well, now we know F is preferred, or A is preferred to F. And furthermore, anything that is less preferred than F, anything that was a descendant in this partial order, also gets dragged down. Okay? So we've now taken away a bunch of stuff that the adversary can do to make W look better than A. Okay? So we want to choose candidates in this set that have a lot of descendants. Okay? Similarly, we can ask, do you like A better than some candidate U? Okay? Little a better than some candidate U. Oh, for you guys over here, right? Okay, and that will drag elements down here if we get the right answer, and so on, and so on. We can ask, is E better than W? You get the point, okay? There we go, okay? So there are just natural classes of queries. We just evaluate these and say which one of these has the greatest potential to reduce minimax regret based on the sizes of these things, okay? And you can show that unless minimax regret is 0, one of these sets for one of these voters has to be non-empty. There's always a query that you can choose using this technique, okay? All right. Now, how does this perform? It's purely heuristic strategy. We know in the worst case you can't do better than full querying, order n squared n. N log n. Okay? I should say that we can generalize the intuitions behind this current solution strategy for asking pairwise comparisons, do you like A better than B, for doing things that we call top T queries, which may be much more natural for a user to answer. So you say, ask a user, tell me your top ranked candidate. The next query that you're allowed to ask is, tell me your second favorite candidate, tell me your third favorite, and so on. Okay? So the same ideas can be applied. I won't describe the strategies that we compare to. One is just randomized, another one is volumetric, which basically I won't explain why it's called volumetric, but basically tries to maximize the number of pairs that you can that are comparable in the transit exposure of your partial order. So basically tries to reduce uncertainty maximally. So we wanted to see how does this stuff perform, both computationally, but in particular in terms of the number of queries needed to get to a good solution. Okay. First data set we looked at is a sushi data set of all things. So 5,000 people, believe it or not, ranked 100 varieties of sushi. They didn't provide full rankings of all 100, but there was a subset of 10 that everybody completely ranked. So we looked at that subset of 10. And imagine, maybe not in Rome, but you want to choose a variety of sushi to serve to 5,000 people at a conference.
Are you going to tell us the top 10?
I'm going to tell. I've got the list of top 10 later. Okay.
It's not going to be served with the coffee break.
The fatty tuna is right at the top. Okay. Just so you know. So what we look at is look at the top 3 lines. I can't work this way. I need one spot.
Okay, look at the mouse on your computer.
What's that?
Use the point of the mouse on your computer.
Oh, let's try that. Okay. But then I have to stand still.
Yeah, I realized.
All right. Okay. So you can see this. Okay. Let's first look at these top 3 lines. Here, what we see is how minimax regret decreases as a function of the number of pairwise comparisons that we ask our population. Okay, and the volumetric and random strategies don't do very well. Our current solution strategy does much better. These three lines show what happens when you ask these top T queries. Notice that every top T query actually implies a whole bunch of pairwise comparisons, so you can't actually, these two sets of lines aren't actually comparable. When you say A is in first place, that gives you m-1 pairwise comparisons that says A is better than every one of the others. But again, we get a fair amount of, separation, although it's hard to see here. Okay. More interesting, we looked at with some electoral data that we looked at from Ireland, where people provided rankings of 12 candidates in particular electoral district. There were actually 30-some thousand votes. People could use truncated ballots, but we focused only on the 3,600 that provided a full ranking of all 12 candidates. And again, we get some pretty nice behavior. The current solution strategy for paired comparisons does much better than the competing strategies. The nice thing about it is it has this nice anytime profile. You get tremendous gains, tremendous drop in minimax regret as you elicit the first few queries, and then it starts to tail off. Now, if you wanted to approximate, I don't know if people want to approximate again the winners of elections, but if you're choosing restaurants, sushi, movies, even certain types of policies, this might be good enough. Finally, we looked at some more synthetic data because we wanted to see how does this thing vary, how does this thing perform as population preferences become more diverse or more similar. So we looked at a model called the Mallows model. Because I'm not going to really talk about learning, I won't get into the details too much. But the idea behind a Mallows model is really quite simple. All right, think of a population that has every person has their own personalized ranking drawn from some distribution. We'll have central or mean, or we'll usually call it the modal ranking. Say A is better than B, better than C. Then the probability that anybody has a particular ranking decreases exponentially quickly with the distance of that ranking from this mean or modal ranking. The distance measure that we use is something called Kendall's tau. So it's basically the number of pairwise swaps, like a bubble sort, that it would take to get from one ranking to another. Okay. Then we've got this dispersion parameter phi, which controls how diverse our population preferences are. It's like the variance in a normal distribution. When phi is 1, preferences are uniform. So you're equally likely to have any permutation as your preference. As this thing approaches 0, people's preferences become more and more alike to where in the limit everybody has exactly the same ranking, and it's pretty easy to make decisions. Okay. This is actually, I think, this is a model that's used a lot in psychometric statistics and now significantly in machine learning. It's not very flexible because of its unimodal nature, but we can. Sorry, I'm talking to these guys. Let me switch for a minute. It's very inflexible because of its unimodal nature, but that's okay. We can just take mixtures of these models if we'd like to be a little more flexible. Okay? And it turns out those can fit. These types of models can fit a lot of different data sets. Okay. So the thing to notice here, I use Tony's trick, the thing to notice here is that as people's preferences become less and less diverse, right, as you converge on a population where people's preferences are very, very homogeneous, it becomes very easy to make decisions. We don't have to elicit much in the way of information in order to get provably optimal wins. Okay? All right. Let me skip in the interest of time. Let me jump ahead to the next topic. How could we exploit these probabilistic models in elicitation? All right. So there's one problem with what I just described. Okay. So it's not a very natural elicitation protocol in certain settings. Okay. So this protocol basically chooses voter and pairwise comparison pairs in sequence. Okay. So I'll ask Eric, do you like A better than B? And we give you an answer. I have to wait for that answer to decide, well, Hector, do you like C better than D? And then Moshe, do you like F better than G? All right, and then I come back to Garrett and say, what about, do you like I better than J? And in the meantime, you've had to sit around and wait before I decided what question to ask you for everybody else to answer their queries. Okay, so the synchronous nature is not very useful and can be very costly. Okay, and in particular, what we have in mind is the fact that if I'm going to engage in multiple rounds of elicitation, there's kind of an interruption cost. In particular, if you have to be synchronized with the responses for other people. Okay, so this one way to tackle this problem is when I come to you, instead of asking a single query, maybe I ask you a bunch of queries. So we're going to focus on this idea of what we call top K queries. So I might say, don't give me your whole ranking, just tell me your top 3. Now I might be getting more information than is actually needed because I haven't waited for Hector's answer before asking Garrett to give me a whole bunch of information. But on the other hand, I've not burdened him with multiple rounds of elicitation. Okay? So there's this trade-off between the quality of the decision that you get, the amount of information that you ask, and the number of rounds. Okay? What we're proposing is have looked at. Oops, where am I going? Okay, what we're looking at is this idea of multi-round protocols where I batch up a lot of information in a way that makes appropriate trade-offs. Okay, so I ask for your top K candidates. I'll stop. Oops, thank you. I'll stop if it's not good enough. I'll stop if my answer is good enough. If not, I'll pick a few more voters, ask a few more queries, and so on. Okay. So even though we've got this very general framework, what I want to talk about right now is on optimizing single round protocols. So the idea is really quite simple. Suppose that I could ask everybody in the room to tell me their top K preferences, okay, or their top K alternatives from a much larger list. Okay, what is the right value of K? All right, and what I need to trade off is what I'd like to do is pick a case so that with very high probability, I'm going to get an answer that has low minimax regret given the information that you reveal. Okay, and this is our goal. Okay, the problem is I can't talk about these questions of solving these problems with high probability unless I have a distribution over preferences. For instance, one of these Mallows models or a Mallows mixture. Okay? But given that distribution, I can now ask a very precise question. What is the minimal K that gives me low minimax regret, say less than epsilon, with very high probability 1 minus delta? Okay? Now, there are many models, probabilistic models of ranking distributions that you could use. I'm going to focus here on Mallows model, but we're also going to look at just subsampling from data sets. In principle, given a closed form model, you could derive analytical results. But the fact is, in principle, you're not going to have these nice closed form stylized distributions. You're going to have a lot of evidence. You're going to have to condition on them, and any analytical results you can derive aren't going to be especially useful. What we're going to propose is a simple empirical sampling-based methodology to optimize the value of this K. The basic idea is pretty straightforward. We're going to sample T profiles from this distribution. The only assumption is that that this distribution is sampleable. That's all I require. Where these profiles come from, it could be a learned model. We could subsample data sets. We might have some generative model that we could use. It doesn't really matter. Given these T profiles, I'm now for each one of them and for each value of K, I'm going to compute the minimax regret for that profile had I elicited just the top K preferences from every individual. Okay, so how good? What would the quality of my decision be if I asked you for your top preference only? If I asked for your top 2, for your top 3, and so on? What this is going to give me is an empirical distribution over minimax regret relative to these T sampled profiles, and with that, I can make a call. Where's the right trade-off between the minimax regret level that I get and the probability of getting that particular minimax regret level? And it's easiest to illustrate with just by visualizing this, by visualizing these histograms. Okay. So here we're looking at randomly generated Mallows models with 10 candidates and 1,000 voters using Borda scoring. And what you see here, if I ask everybody, I forget how many profiles. Oh, it must be 100 profiles. If I ask everybody just for their top preference, I cannot make a good decision. On the scale of 1 to 10 of the Borda score, my average minimax regret per voter is greater than 4, right? I'm nowhere near optimal. But if I ask people for the top 2 preferences, I'm going to go to this side, for the top 2 preferences, minimax regret drops, okay? And it's now down to around 2, and now I'll use Tony's trick. If I ask 3, it's now, on average, minimax regret is less than 1, and the odds of it being greater than 1 are quite small. And if I ask 4, you get the point, okay? So you get these empirical distributions. And you can make the call, depending on your application, as to how precise you'd like to be, what level of error you're willing to live with, and with what probability you're willing to go above that particular error limit. Okay? Now this can be used purely heuristically. You can plot these things in different ways. All right. I actually think using this, just eyeballing these histograms is probably a reasonable way to do it. But you might ask yourself theoretically, what confidence can I have in the decisions that I'm making? And that's just a standard PAC style sample complexity question. So if you're so inclined, I don't expect you to even try to parse the details, but if you take a particular target epsilon, decision quality, and confidence parameter delta, and say, I want to be sure that if I pick the minimum k according to some formula, if I generate t samples, okay, I can say with very high probability I've gotten the right answer by generating simply enough samples and choosing the empirical minimizer. Okay. Okay. You can do this with synthetic distributions, with random models. You can actually do it with data sets. With the sushi data set, for example, we took the 5,000, broke it up into 50 profiles of 100 voters each. Okay, and you can do the same sort of thing. You can see here for sushi, you're probably okay living with a little bit of error. So you probably only have to ask people for the top 3 or 4 preferences out of the 10 varieties. For the Dublin data set, preferences are a little more diverse, so you've got to go a little bit deeper in the ranking. But with very high probability, if you ask for their top 6 preferences out of the 12, the top 6, you're going to get low minimax regret, and you're almost certainly going to get optimal if you ask for the top 7 preferences. Okay, so this gives you a way for deciding, how much information should I really dig into. I'm just going to spend about 1 minute talking about learning. A natural question now. We've got robust optimization. We've got elicitation. We've got a way of exploiting probabilistic information to make elicitation more effective and to help us make various types of trade-offs. Fourth question is to ask, where do these probabilistic models come from that you want to exploit in developing these elicitation protocols? Okay. Well, it turns out that these things can be learned from sample data, from historical data, from behavioral data. You put people in choice situations and look at the choices that they make. All of this is naturally represented in terms of pairwise comparisons. Somebody likes A better than B, what an economist would call revealed preference. Okay? Learning these distributional models, these probabilistic models from such data is a very hot topic. It's been studied for decades in psychometrics and econometrics and statistics, and now in the last decade and a half, to a great extent in the machine learning community. Okay. Basically, you can boil down learning of these models into two components. One is an inference component, given a probabilistic model and some evidence in the form of, say, the partial information about a voter's preferences. Can I get a posterior over their actual true underlying preferences? And the learning problem, which says, given a bunch of this data, what is, here we focus on Mallow's models and Mallow's mixtures. What is the model in my class that maximizes the likelihood of my data? Okay? And you can generally solve these learning tasks using an algorithm known as expectation maximization, as long as you can solve the inference problem. Okay? So it really comes down to making inference in these models much more tractable. Okay? Turns out it's almost always difficult, but there are things that you can do to approximate. So I'm going to skip over that. These are your top 10 sushi function. Okay. This is just a mixture model that one can learn from the sushi data. Okay. Anyway, I just want to point out that learning of these preferences is a problem that gets a lot of attention. There's a lot of great progress that's been made, but I still consider it largely to be an unsolved problem from the perspective of social choice. Okay, in the last couple of minutes, I just want to mention a few dangling issues, things that I find interesting, and the first one I think many in this community would find interesting. Okay, everything that I've talked about so far has focused on what I'll call atomic choices, atomic options, or atomic alternative sets, right? Sushi 1, sushi 2, sushi 3. Okay? But very often, if we're talking about schedules, producing, configuring products, people have talked, no, Jerome skipped that. But Laurent talked about multi-issue elections where you're choosing, say, politicians based on their stance on a variety of different issues. It's now a multi-attribute configuration problem. And people will have different will have preferences over this much larger, much richer outcome space. Okay? Of course, representation is a key issue. We've heard a little bit about CP nets at this conference. Something that to be honest, even though my name is associated with it, I'm not a big fan of the representation. Now here's the key question. In single agent problems, when we've got these multi-attribute combinatorial domains, minimax regret is actually proven to be pretty valuable from the perspective of both robust optimization when you've got imprecise information about utility functions, and from the perspective of elicitation. This whole current solution idea actually applies and works reasonably well. Okay? We've applied it to a variety of domains: product configuration, combinatorial options for sourcing and procurement, autonomic computing, and things of that nature. So here's a key open question, one that I'm very interested in. Do the optimization techniques and the elicitation techniques for these multi-attribute spaces extend naturally from the single agent case to the multi-agent voting case? Okay, and I'm not sure what the answer is. Just to give you a flavor of what these techniques look like. Let's imagine we've got a combinatorial optimization problem, multi-attribute optimization problem. We've got a set of attributes, think of them as Boolean features, say these xi's here, and we've got a weight vector or utility vector, think of it as corresponding to an additive utility function, wi, and we want to maximize for a single user, we want to maximize the choice of this product given their utility function, but subject to some feasibility constraints, okay? So we can't pick arbitrary configurations, okay? The problem is, when you're in a preference elicitation setting, you don't actually know what the parameters of this utility function are, right? Generally, if you ask pairwise comparison questions or other types of questions, though, you do get linear constraints on the values of these weights. If you say A is better than B, then it imposes a linear constraint on this space, of utility functions. All right, and then our optimization, don't worry too much about the details, but we can do the same minimax regret type of optimization. Okay, so we want to find the feasible product that minimizes the adversary's ability to make me regret that product, where the adversary is choosing a utility function from this polytope and a different configuration that's optimal. Okay. All right. Now these are very hard computational problems, but there are a lot of techniques from the math programming and operations research community that you can actually bring to bear. Okay. And it works very well. You get these nice anytime profiles in terms of elicitation, in terms of computation. You get the same types of elicitation curves. Okay, and we've actually looked at some user studies for these and found that people are very comfortable with the idea of minimax regret. But now, what can we do if we want to apply these techniques to the voting situation? Okay, it's an open question. Okay. And here, in the interest of time, I won't go through these things, but there are a lot of challenges, right? How do we extend these optimization techniques? How do we reduce the elicitation burden where the queries that I asked Jerome might depend on the answer that Garrett gave me to some of those questions? Do you vote on things sequentially, kind of work that Jerome has done? If so, how do you optimize the order? Things of that nature. A lot of very interesting questions. Okay. How am I doing for time?
5 minutes.
Okay, good. I'll take about 3 minutes and talk about one other set of open issues. Again, this is also a very hot topic in a lot of different communities, and that is decision making and recommendation and things like that on social networks. Okay. Now, what does this have to do with voting and preference elicitation? Right? And so let me tell you. Let me give you my thinking. All right. So you guys all know what social networks look like, and I'm sure you're all familiar with the fact that people are convinced that social networks shape people's behavior. The idea of homophily, that people that are attached to the social network tend to exhibit similar behaviors, is very well documented, and there are a number of explanations for why this might be. What is also often claimed, but as far as I know, hasn't really been documented that substantially, is that people's, not just their behaviors, but their preferences are actually correlated when they're connected in a social network. Okay? But I've seen very little evidence that say preferences, where the way we think of preferences, either some ordering or a utility function, are actually correlated. Right? The actual observed correlations tend to be at the level of behaviors. Okay? But if it were the case that preferences were correlated, then social networks would be an incredibly valuable source of preference information and could make our job of making recommendations, either individual or group recommendations for specific individuals, much easier, because I could elicit much less effort, right? So Gerhard has certain preferences. I know he's connected to Hector, so that gives me some confidence that Hector's preferences for I don't know what wine you drank last night, but might be very similar, okay? And that can reduce the elicitation burden, okay? I think it's an incredibly interesting and challenging research problem, okay? But I think it involves getting psychologists and sociologists involved to tell us exactly how these correlations, what these correlations look like, and to help us develop probabilistic models of correlated preferences. Okay? Last point that I want to make is that social choice problems, apart from just giving us information about preferences, social choice problems are often arise in a network context. Okay, and increasingly we're seeing a lot of people looking at things like allocation problems, assignment problems, matching problems in the context of social networks. We also see a lot of study of voting on social networks. How does the voting behavior of people in my circle influence my specific choices? Okay, so one thing I just want to throw this out here as kind of a toy little problem is something that we've been thinking about I've been thinking about with one of my students. It's called voting with empathetic preferences. Okay, so basically in this model, the idea is that you're going to trade off your own intrinsic utility for, say, going to a particular restaurant with those of your friends or neighbors or acquaintances. Okay, so for example, suppose that I like a particular restaurant A better than B, better than C, better than D. Okay, and so this might be the way that I'd like to vote. Okay, however, I'm going to dinner with Hector and Gerhard. Okay, and I'm going to be sitting around chatting with them a little bit, and I know, maybe I know or I don't know, they like B, which is my second favorite choice, but they really hate A. Okay, so if I'm going to be sitting at dinner talking with them, maybe I'm not going to have such a good time if they really don't like the food that they're eating or don't like the atmosphere. Okay, so I might be willing to sacrifice my own intrinsic preference for A and say, no, I'd be pretty satisfied with B. And I'll tell you that the first inkling I had that this actually occurred was putting our group recommendation little prototype in front of my wife, who, when she looked at the votes of her sisters, said, I would change my vote because they won't be happy if we go there. Okay. All right, but now you get into this problem. Now Hector has his friends and acquaintances, and he might want to defer some of his satisfaction to them, and Gerhard, same thing, and their friends depend on their friends, and we get this whole circular causal chain. How do you go about voting? Okay, now you don't want to put people in a situation where they have to think about very deeply about what the preferences of their friends are and what the preferences of the friends of their friends are, and so on, to figure out how they should vote. But it turns out you can just solve this whole thing. People don't have to know their preferences. It feels a little bit like PageRank. You just solved a simple linear system and basically turn this into a simple weighted voting problem. Okay. Now, we actually think that this kind of thing goes on fairly regularly, where people are adjusting their votes depending on the preferences of their friends. If you want to help people with this challenge and not having to have to think too strategically about what's happening down the road, we're now faced with a number of new elicitation and optimization challenges. Okay, so I just want to throw that out there as a potentially interesting problem. Okay, so let me wrap up. Last slide. I won't say much. Let me just say that what we've embarked on, I believe, is just a starting point for applying probabilistic modeling methods, machine learning methods, and decision theoretic optimization techniques to not just voting problems, but potentially a wide variety of social choice problems, a lot of fascinating elicitation and optimization questions. As you move to combinatorial domains, I think a lot of interesting representation questions that would be of interest to this community. And of course, since this is just a starting point, there are a number of next steps. I won't go over them. I'll just put them up there for you to take a look. Okay? Thank you.
Thank you very much. Okay, I guess to characterize your scientific development briefly, one could say from NMR to MMR, right?
There we go. Very
Okay, we
good.
have time for a few questions. Yes.
Okay, yeah.
Look, according to the question, when the idea of sampling is social choice, I think the first time I encountered it is an old science fiction story by Asimov, where to elect a president, you sample and you choose one person in the whole United States,
Right.
and you ask them to make a choice.
That's it. Randomized dictatorship.
Sample one person.
That's it.
And you let them.
That's it.
My question is, I actually personally love board. I think it's a wonderful rule.
Yes.
But I've run into the point of using it where you have incomplete information, but one that cannot be fixed by elicitation. Because the problem of conflict of interest.
Okay.
You have to choose for usually some kind of recognition or honor.
Yeah.
And some people say, I cannot have an opinion about this or that person
Right.
because of conflict of interest.
Mhm.
And I have not found a good solution. Then elicitation is not an issue.
No. So,
But I have not found a good scheme of dealing with it. With this kind of incomplete, where you know that this is it, there's no more information.
right. So is the real question is what is the issue that you're trying to
How do I
resolve?
what would be the
Do you-
border rule for when I have incomplete information, but
What-
that cannot be, I'm not allowed to ask more questions there.
Okay, but do you want to actually account for the preference of this person who doesn't want to reveal?
No. But
Oh,
on one hand,
so-
if you say that the people they cannot vote on, you put them at the bottom,
Right.
you're kind of penalizing them in a way that it doesn't seem quite fair.
Oh, sorry, I see. So it's not that they're not participating, but they're voting on a subset.
They're voting on a
Voting
subject.
on a
They're not allowed to vote on the full.
That's a good question. I've never thought of that. In fact, so we just had a paper at EC where we've kind of discovered that board actually is a very robust rule if you're trying to do things like maximize social welfare, given some latent utility functions. In the population, board does a surprisingly good job at that. My one reaction would be, can you actually take this incomplete information and simply use it as evidence for the true underlying ranking, okay? And then, just kind of average those scores somehow, right? That's my natural reaction. This partial vote where I've left people out is just simply gives me evidence, and given the rankings of other people, I've got a posterior over what their true score might be, and I kind of take an average score of that. That's my first reaction, but it's a hard one.
One more question?
I would like to know more about the motivation behind the choice of minimax regret,
Right.
which is somehow pessimistic assumption, and whether this is, is it for the intended application or is in principle a good measure?
Yeah, so I don't view minimax regret as pessimistic. I view maximum as pessimistic, right? Minimax regret simply says, look, whichever candidate that I choose, if I have no information about what the completion of the underlying profile is, and the other candidate can have not a worse score. We're not talking about what the score is. We're talking about how far it is from optimal, which is what makes it different than maximum. Okay. Now, if you have a prior over the underlying vote profiles, I'm perfectly happy to maximize expected, the expected score. Okay. But the nice thing about minimax regret is that when you use it coupled with elicitation, right, what it does is it identifies those aspects of your uncertainty where if I got a little more information, I'm actually provably increasing my ability to make a good decision, right? And so when you get these anytime curves, I think it's more than a robust decision criteria. I view it as a very useful driver of elicitation.
Last question.
Yeah. Actually, I have two very fast questions. So one is, do you think that any of the insights you gave in the first part of the talk will help also on the problem of computational algorithmic games in the presence of partial preferences relations?
Sure. So you can compute, say, Bayes-Nash equilibrium, right? Bayes-Nash equilibrium in a game, equilibrium in a game, usually assume like nobody knows what the actual type is. You can actually use minimax regret. We've done some work probably about 8 years ago on what we call minimax equilibrium, where the player will choose an action, not knowing what the utility function of the other players is, will choose a robust action relative to that uncertainty, right? And then you have to find the strategy. So yes, you can apply these techniques. Tenenholtz and Boltzmann, they had, they call these pre-Bayesian games. Right? These are Bayesian games where you don't give me distributions over the types, you just tell me what the set of types are. And yes, and that's
Very good.
Yeah, but have you thought about any issue of strategic process in this setting?
Oh yeah. All right. So manipulation, right? Look, manipulation is an issue. So strategy, for those of you not familiar with social choice and mechanism design and so on, one of the issues here is that people might misrepresent their preferences in order to drive the outcome in a way that's actually better for them. Okay. The fact is that that's unavoidable, right? There are theorem, the Gibbard-Satterthwaite theorem says that there is no way to do it if you've got more than two outcomes, and you don't tie people's preferences down, right? Now, does this give you new opportunities for manipulation? Absolutely, okay? Am I concerned about it? Not so much, because we've been doing some empirical work on how likely manipulation is under realistic knowledge assumptions, and we actually don't think manipulation is as severe a problem in practice as social choice theorists would have us believe. But that's a discussion we can have offline. Yeah.
Okay, thank
Good,
you very
thanks.
much.